Hello, everyone, and welcome to the podcast. My name is Kishan, your host, and today we have a very special guest, Dr. Xiaoning Hu. Dr. Hu is currently working as a postdoctoral researcher at Peking University, China. He received his bachelor's degree in materials engineering from the Nanyang Technological University, Singapore in 2016, and his PhD also from NTU in 2020. Doctor Hu's research interests have focused on the characterization and processing of graphene and other 2D materials. He has 3 patents and has published more than 15 peer-reviewed journal articles. He has received numerous awards such as the PRC Scholarship and the NTU President's Research Scholar Award. Dr. Hu, it's a pleasure to have you on the podcast. How are you doing today?
Yeah, pretty good. Hello, everyone.
Thank you very much for joining us. And looking at some of your recent works, it's evident that you have spent quite an amount of time working with CVD graphene transfer processes. So we would like to perhaps begin with the question, what is CVD graphene transfer process?
So normally, we have the CVD graphene. CVD graphene by what literally means is you use a chemical vapor deposition process to fabricate graphene film. But normally it's on the metal substrate. But when we talk about the application of this CVD graphene film, normally we cannot just directly use it on the metal substrate. We need a transfer process to transfer this graphene film from the metal substrate to another functional substrate. For example, silicon substrate, plastic substrate. So we need this transfer process to transfer graphene film from one substrate to another kind of substrate. So this transfer process is critical because the CVD graphene is only one atomic thickness. You need this process to be very cautious, and you need to handle it in handle it cautiously, and to prevent it from the crack or contamination. And finally, you get the graphene on the destination substrate. So that's basically what the transfer process means.
Very interesting. And what type of improved graphene transfer processes are you currently working on?
So in recent years, people have developed so many different kinds of graphene transfer method. So normally it can be categorized into 3 processes for this transfer process. First, you need the delamination process of the graphene from the metal substrate, and then you need to laminate the graphene onto the destination substrate. Also, during this process, you need some transfer medium to help you to handle this graphene. So at the end, you need to remove this transfer medium from the graphene surface. So people in the past, people have used some oxidizing method. That is to dissolve the metal substrate by using some chemical agents, or they can use the electrochemical bubbling process and to delaminate the graphene from the metal substrate. But this process always involves some solvent, and you need to be very cautious, and it's very difficult to handle through this process. And because it's always related to the solvent, normally people say it is wet process. When it is this wet process, and it's it's very difficult for people to operate. And so now what we are focusing on is to try to make this process more easy to handle and use shorter time, and to use to try to involve more dry process in this whole transfer process, and to make this transfer process scalable and easy to handle. That's what we are trying to improve. But that always also means we need to develop some new transfer media, and to find an easier way to delaminate the graphene from the metal substrate, different from the conventional oxidizing process or the electrochemical bubbling process.
Could you provide a bit more details on the type of transfer medium that you currently use?
Now we trying to use polyvinyl alcohol. Also add some small molecule into this polyvinyl alcohol.
And any particular reasoning behind the use of PVA? Because one of your recent or article that was published in 2023, for example, reported on the use of PPC. And it seems that now you have moved on to another interesting polymer, PVA, which has also been has been used for different types of CVD graphene transfer process. So any particular reason why you chose PVA in this case?
So we also add some small molecule into this PVA transfer medium. We want like what I just said, we want to have some more dry process in our transfer process. So after when we use this PVA and this small molecule, the composite as our transfer medium, after we delaminate the graphene from the metal substrate, and then we laminate the graphene onto the destination substrate. And then we can have a low temperature process and to induce a cross-linking of the polymer chain. And then the interaction between the PVA and the graphene will be decreased. And then we can directly peel the PVA off from the graphene. So we can, in this case, we can, we don't need the dissolution process anymore, because normally when we want to remove the transfer medium from the graphene, we always use the organic solvent to dissolve the polymer transfer medium. But when we use this new transfer medium, also the new transfer process, we can avoid the polymer dissolution process. And this is the all-dry transfer process. So in this way, the graphene can be transferred in a more quick and easier to handle by this transfer method.
So it's very interesting that you mentioned that, and it seems that now you are moving on to a fully dry transfer method that does not require solvents. Is that correct?
Yeah, during the transfer process, we don't require the solvent. But when we do some pretreatment, for example, when we want to decouple the graphene from the gross substrate, when we do the delamination procedure, we still need some solvent to pretreat the CVD graphene wafer.
Right. So what type of solvent do you need during that particular process of pre-treatment of CVD graphene when it's directly on the copper substrate?
We use a mixture of ethanol and water.
In this case, is it some form of an intercalation technique that you're seeking?
Yes, this is kind of an intercalation. By immerse the CVD wafer film into this mixture, there will be a layer of copper oxide between the graphene and the metal substrate. So the interaction between the graphene and the copper substrate will be decreased.
And how do you control the oxidation of the copper underneath the CVD graphene film?
So this is also comes from this idea is also comes. We do some improvement on this oxidation. Actually, in this graphene transfer field, there is a conventional method for the oxidation. Oxidation is not something we come up first. People use the water previously to oxidize copper, and they found it's effective. But if only use water, the oxidation will be non-uniform. We found based on our experiment result, we also tried this method, but the oxidation is non-uniform. So we add some ethanol, the organic solvent, into the water, and then we tune the ratio between the ethanol and water, and we want to make this oxidation layer more uniform. So that's what we do. And based on our experiment result, I think by using our method, the oxidation layer is quite uniform now. So during the delamination process, the graphene will be crack-free, so there won't be some defect or crack after the delamination.
And what is the time scale that is required for the oxidation process?
Basically, we use 10 hours to oxidize copper wafer film.
So this we are talking about half a day.
Yes.
Okay. Yes. And is this reproducible across several substrates?
Our products mainly focus on the copper wafer. We only use this method for the copper wafer. So other metal substrate, I have no idea whether it can be reproducible. Okay. But copper is effective. Also, I want to add some information. Now we also have some other intercalation technique, like we use some small molecule. We want use some small molecule, and it's also effective for intercalation. Mm-hmm. So it doesn't need the oxidation process. It can be faster than this ethanol and water mixture.
And this particular, let's say, molecular intercalation method that you're mentioning, is this in a dry environment, or does it also require a liquid?
You still require liquid. So we cannot totally avoid the liquid through the whole process. But that's very difficult. We still need some effective decoupling method. So far, what we can do best is to have a pretreatment process first, and then we do the transfer.
During the pretreatment, it is as you mentioned, it is helpful to have the oxidation of the copper substrate using a mixture of water and ethanol. Mm-hmm. And after, let's say, the delamination of the graphene film, how do you remove the transfer medium?
So for conventional method, the most commonly used method is to use some organic solvent to dissolve the polymer. But in this way, definitely there will be some polymer residues left on the graphene surface. So the cleanness of the graphene will not be guaranteed. So now we need to have some, let's say, the change on the temperature. This kind of external condition change on this graphene and the transfer medium, especially the transfer medium, to induce some structure change of this transfer medium and to alter this interaction between the transfer medium and the graphene, and decrease the interaction between the transfer medium and the graphene, and then we can use the direct exfoliation process to remove this transfer medium. This is the most ideal way to do the removal, to conduct this removal process. So far, we have achieved this by using the freezing method. We put this polyvinyl alcohol transfer medium in a very cold environment, and freeze it, induce the cross-linking between the polymer chain, and then we can directly exfoliate the polymer transfer medium from the graphene surface. Then the cleanness will be improved.
Very, very interesting information. What is the time scale of the cross-linking process?
I think about it's still hour scale. I think half an hour, about half an hour.
Okay. So in such a situation, what is the typical time required for performing the transfer from having, let's say, the pre-oxidized substrate in hand?
You mean by using this new method?
Yes.
I think maybe in 1 hour should be should be enough.
And here we are talking about a 4-inch wafer scale, or what is this dimension of the transfer?
4-inch scale.
I'm curious about what is the process to remove or delaminate the graphene from the copper substrate.
So just use the mechanical exfoliation.
Okay. And this mechanical exfoliation is triggered by freezing.
This process doesn't involve the freezing. The mechanical exfoliation of the graphene from the copper, from the oxidized copper. First step, we need the oxidation process to decrease interaction between the graphene and the metal substrate. Then we can we need to add the transfer medium on the graphene. We do some spin coating or other kind of coating process. After we have this transfer medium, we need the help of this transfer medium, and then we can. Normally, we also add some supporting film on the transfer medium. For example, like the transfer release tape. And then with the tape, we can exfoliate the graphene together with the transfer medium. And then easily, because it's already decoupled, the graphene, the interaction between the graphene and the metal substrate already decoupled. So you don't need so much strength, and just easily to exfoliate the graphene from the metal substrate. Then the delamination process is completed. The reason we prefer this delamination process is also because if we still use the previous transfer method like the oxidation method, or just dissolve the copper into the solvent, that means, and also the electrochemical bubbling method, there are so many solvent processes involved, and it's very difficult. Also, the cost will be so much because you need to treat those solvent, harmful solvent. So by using this delamination process, we can realize the scalable transfer process.
And in terms of polymer contamination, does the transfer medium that you use leave behind residues that influence the electrical transfer of the CVD graphene films?
Yes, it will have some influence. But if you have the polymer residues, the polymer can sometimes doping on the graphene film, and also the carrier or inside the graphene film, and it will definitely lower the carrier mobility. So normally during the transfer process, we need to avoid this kind of residues.
Right. And in your case, how do you make sure that you have ultra low residues on the CVD graphene film?
So we think the best way is to avoid the dissolution process. So if you can imagine if you use some organic solvent to just dissolve the transfer medium, definitely there will be easily some, not all the polymer can dissolve into the solvent. But whatever kind of method how careful you treat this process, that it's always will be some. So if you can just change the structure, the molecular structure of the transfer medium, lower the interaction between the graphene and the polymer medium, and then you just exfoliate it off from the graphene surface, that will be best. We also have some experiment results about this, compare the polymer dissolution process and this kind of exfoliation process. The exfoliation will be better.
How does the mechanical delamination process that you have just talked about compare with the electrochemical delamination process?
You mean which step? I'm talking about is this the delamination of the graphene from the metal substrate? Are we talking about this process or the remove of the transfer medium? Because the electrochemical process is only for the delamination of the graphene from the metal substrate.
Right. I'm curious how these two different transfer processes compare.
I think, of course, both they are effective delamination procedure. But the electrochemical bubbling method, normally we need to use some the strong basic solvent, like a sodium hydroxide. Normally we use, and after the delamination process, electrochemical. Not mention the complex, because you need the electrode, you need to apply the voltage. The experiment setup will be complex compared to the mechanical exfoliation. And after this electrochemical bubbling process, because you use the strong basic, you need to have a cleaning procedure to avoid the metal ions contamination on the graphene. So you need to clean it. Use some time, also a complex procedure. And finally, also the strong basics, when you do a large scale of the transfer medium, you need to consider the cost of the treatment of this kind of usage of the strong basic solutions. So we think the mechanical exfoliation process will be more cost effective with a shorter time. So we prefer this mechanical exfoliation procedure. But also the tricky part is we need a decoupling, of course. So far we still need the decoupling method. But I think totally we consider all the aspects of the pros and cons. We consider them together. I think still mechanical exfoliation is better. Especially when we talk about the scalable transfer, because that's the ultimate aim of the BGI, with what we want to do about the graphene transfer. So we think only the mechanical exfoliation is compatible with the scalable process. If we insist on the electrochemical bubbling process, the conventional method, we don't make any change, I think the scalable will be very difficult.
How do you characterize the CVD graphene films that has been transferred using the mechanical delamination process?
Characterize the techniques. We need to avoid the crack, and also we need to be quick after the growth of the CVD film on the metal substrate is a very complete film. We cannot say after transfer, it becomes part. This only transfer part of it. So as the first, we need to guarantee it's complete. We need to make sure it is intact, and we normally use the optical microscope as the first to make sure there will be no damage or some part of some part of it is damaged. Normally, optical microscope can already guarantee about that for that kind of dimension scale, like micrometer scale. There is no damage. And also, we need to use Raman spectroscopy to detect if there is no defect on the molecular structure scale. Also, from the Raman, we can measure the doping level, strain level. We want no doping light strain of the graphene film.
Type of doping density or strain do you observe in these type of CVD graphene film that's transferred using your method?
We compare our method with wet transfer. For example, the delamination by the oxidation process, and then use a wet transfer process to transfer the graphene film. We compare our mechanical exfoliation method and the wet transfer process, and then we check normally we compare the 2D peak of the graphene by using the Raman spectroscopy, and to see from the four ways at half maximum. And we compare ours have a smaller 2D four ways at half maximum. That means we have a better quality. Also see from the position of the G band and the 2D band. And I think our compared to the wet transfer process, our graphene film have less level of the doping stream. We can normally we do is comparison between the other process.
In terms of upcoming challenges within the CVD graphene transfer process, do you foresee additional challenges that are pending in this particular domain?
I think it's still actually still a quite challenging technique so far. I think because graphene is only one atom thickness, and we still need to be very careful through this transfer process. So let's say if we want to do the scalable transfer process, we want our transfer process to be robust and highly repeatable, and also the large area transfer of the graphene film. I think is still quite challenging. So we still need some very robust transfer process to finally achieve the scalable transfer of the large area graphene 3D graphene film. I think we are still making effort on that.
And moving forward, what are you most excited about?
I think, let's say, if we have this, we can finally realize this. We can finally develop by whatever method. We can finally achieve the scalable graphene transfer. That's very exciting. So that means we can. I think that means we can already integrate the graphene film, the CVD graphene film, into some pilot scale. It's at the industrial level, I think. Yeah, am I correct? I think that's what I foresee. If we have this kind of transfer technique. Also, I think beyond graphene, if we can have some universal transfer technique for this kind of layered 2D material, not only graphene, we can, let's say, also transfer some MOS, this kind of layered 2D material, and we can do, we can definitely we can develop, we have this. That means we have this that kind of foundation, the material foundation. From the material perspective, we are able to integrate 2D material and into some, let's say, the silicon industry or other industry to finally find some scalable application of this kind of 2D material. So definitely that will be very exciting. But of course, this process will be very challenging. Because we do the transfer process, we know how difficult it is, especially when you handle this kind of very, very thin material without crack, with very high cleanness. That's very challenging, of course.
Excellent. So, Dr. Xiaoning Hu, thank you very much for joining us on this podcast.
Yeah, thank you, Dr. Kishan. Thank you for me this opportunity to join this podcast and to share some of my experience, also some of my point of view about the graphene transfer.